Hello, and welcome back to Chapter 19. We're moving on in this section to talk about weather fronts, and we'll start with its kind of description and an anatomy, really, of what those weather fronts are, how they're constructed and organized in a basic sense, and then we'll move on to fit them together with the mid-latitude cyclone. One thing to keep in mind is that we just talked about air masses: maritime polar, maritime tropical, continental, tropical, and continental polar. Those were the main ones. And so it's those air masses that are coming together at different places throughout the Midwest, through what we call the mid latitudes, right? And ultimately creating what we call the mid latitude cyclone, and it is a kind of model for a lot of the atmospheric conditions that we see in this region. The first is the warm front. The warm front is characterized by two different air masses, right? So on the right-hand side, we have cool air, and on the left-hand side, we have warm air. And that means, ultimate sources for, let's say, the warm, moist air in this case, that would be Gulf air pushing up from the Gulf of Mexico through Texas, through Oklahoma, and sort of meeting up with the cold air mass, which is typically cold and dry. And that cold air mass could be maritime polar, or it could be continental polar. Maritime polar coming down from the Pacific Northwest, or the continental polar or continental air mass coming down from the north. And what will happen in this case is that we have warm air that is moist but it is more buoyant than this cold air. And as the warm air catches up with the cool air, it rises, and as it rises, it reaches a condensation level, which you'll remember from chapter 16, chapter 17. And as it reaches condensation level, it starts to produce clouds. Well, because the air is rising at a relatively slow rate along a gently sloped boundary, notice how this boundary is not very steep. We'll compare it to a cold front in a little bit. That means we get gentle rain, we get calm wind conditions, because if you remember, the air in here has time to cool off as it's rising. And that has, if you'll go back to, say, chapter 17, where we talked about environmental lapse rates, in which the cloud cools down a little bit more quickly or a little bit more slowly than the surrounding air mass. And so this is a gentle situation when the cloud is rising up. It is producing a number of different kinds of clouds. So remember from our discussion, nimbostratus clouds. Nimbo means rain, so we have layered rain clouds that are low. But as it rises up, we form altostratus, altocirrus. And these two clouds are sort of start out as a mixture of rain, they move to ice, and these high altitude finally here, cirrostratus and cirrus clouds, those are the wispy ones, are constructed of ice. Okay. One important thing to know also before I move on is the shape of this little symbol here and its color. Warm fronts are typically depicted as a line in which the warm and cold air are intersecting along the Earth's surface. So there's warm air above this in this area up here, but really that boundary, that front boundary, is back here where the intersection occurs at the Earth's surface. And this half circle here indicates a warm front, and the circles point in the direction that the front is moving. So there are things called stationary fronts, but in this case, warm air catches cold air and is moving up over it. Opposite to that, we have something sort of antithetical, at least. We have a cold front. Now, in this case, you'll notice the symbol has changed, as well as the color. Down here, we've got these teeth, which point again in the direction of flow. But what is happening is that we have cold air, which is dense. And that cold, dense air is catching up to this warm air mass, right? So cold air could be an air mass such as the continental polar air mass, and the warm air mass might be a marine tropical marine tropical air mass coming together. In this case, the cold air mass is plowing into the warm air mass, and it is denser, and so it stays close to the ground. And the effect of that is to push the warm air up. And we are seeing this kind of front develop in Illinois. We're right now, and we're in that season, tornado season, and we're seeing a lot of thunderstorms develop. And those thunderstorms, you can see here, are caused when that warm air rises very, very quickly. It stays warm, right? So its lapse rate is much slower than the environmental lapse rate. So it stays warm as it moves up, creates condensation, and creates thunderstorms, large size hail, and eventually tornadoes. And so the locus of rain is at the boundary here, right? And if we back up just for a second, notice rain is extending over a larger area when we're dealing with a warm front. We're going to expect heavy precipitation over a very short time in this case. And if we back up here, we're going to expect lighter precipitation in the warm front over a longer period of time. Okay? And the primary clouds here are cumulonimbus clouds. So those were vertically distributed clouds, puffy clouds that typically end in this, what we call the anvil shape, the anvil head shape, where the upper part of the cloud is strung out, in this case to the right, as it gets up into or near the boundary between the troposphere and the stratosphere. The key here, what drives this system and makes this such a potentially violent situation, is that we have this very steep boundary, right? So this is steep. And in the warm front, it's gentle, and that has a lot to do with how the clouds will cool and where condensation level is going to be reached. Okay, now this other here, the occluded front, this other type of front, the third front that makes up the mid-latitude cyclone, is composed of both fronts coming together. So cold front here on the top left diagram, hitting the ground right there, and there's a cold front there, or a warm front there, right? And so what's between these two cold air masses is a warm air mass. And so when you get an occluded front, what is really happening is one cold air mass is catching up to another cold air mass, and they're intersecting. That traps the steep boundary here and gives us the gentle boundary there. But what we end up with is combining cold and warm front characteristics. And so we get wide areas of rain. We get intense rain in some locations and gentle rain, right? So in other locations. And that has to do with the fact that we're sort of sandwiching this air, this warm air that's carrying most of the moisture between these two cold air masses. Okay? So the two air masses that come together to start this process are going to start out as something called the stationary front. And I'm not going to get into the details of it too much, but you can see right here we have the half circle on one side and the tooth on the other. So what's happening here is at the stationary front, we're not dealing with, and I'm going to go ahead and erase this really quickly, we're not dealing with a situation in which we have air moving across the boundary or even really vertically. What we have is, at a stationary front, air moving side to side, right? Side to side, kind of like a transform boundary or a transform fault. And it's when we start to develop a kind of rotation in the system, okay, that cold air is going to come around and start to push on the warm air. And as it does that, as that rotation begins, then we start to see the development of the mid-latitude cyclone and the development of both the cold front and the warm front. So in the early stages, the cyclone will have a cold front, which you can see here, and then we'll have a warm front, which you can see up here in the right-hand side diagram, and they're very separate, right? Rotation has begun. Now, I'm going to erase this for a second. As the cold front starts to advance, it's moving a little bit faster than the warm front, right, off to the right, or to, typically in our neck of the woods here, it's to the east. Okay, as it advances, what it ends up doing is catches up with the warm front. So cold front catches up with the warm front and creates an occluded front that's down here. And the occluded front is shown in purple, and it is shown as a mixture of the half circle and the tooth alternating, but both pointing in the same direction. Okay, so it's different than your stationary front. Now, this occluded front is going to grow with time as the mid-latitude cyclone evolves and rotation in the cyclone continues. This rotation, this counterclockwise rotation, occurs because this is affected by the Coriolis effect. This area here within the occluded front, or at the sort of tip of the occluded front, is your low pressure zone in that area, or actually even down here would be a low pressure zone as well, and that's drawing air into the system, or drawing in air masses into the system. But as this occluded front gets longer, the system is going to begin to evolve into its sort of past its mature stage, and it's going to eventually dissipate. And what causes this to dissipate, is, if you'll remember, is that the occluded front is the sandwiching of cold between, or warm air in the middle between cold air on either side. And what happens is that these two things push together eventually, so that ends up looking like this. When this cold air mass moves to the right and this one continues to move to the right, they push into each other and they meet up. And so you get cold meets up with cold to create a cold layer on the bottom. Well, cold air likes to sit low because it's more dense. However, on the top, we end up with a warm air mass. Now, stratification like this takes all the fun out of rearranging the air masses. So in order to create those strong winds, we need vertical movement of air, right? Because we need to effectively move warm, high-energy material up into the upper atmosphere to drive winds and thunderstorms. When stratification occurs like this, there is no vertical motion anymore. So the kind of gradients and energy that were present in the previous stages of the mid-latitude cyclone have now dissipated and are done, or are over. Okay, we can look at some examples as this thing would move across the Pacific from the Pacific Northwest through the mid-latitudes, sort of south of the Great Lakes. So here we are up here around the southern tip of Lake Michigan. You can see we start out with a stationary front. That's side-to-side motion, and the system begins to develop some rotation as different parts of the front are moving at different velocities. We also have something called the Coriolis effect affecting all these systems. And so down here we begin to see that rotation again. Okay. Early stages of the actual cyclone have evolved here in step 3, where we see the fronts that have developed. Here's the cold front and the warm front. And then as it evolves, we see that the system, the low pressure system here, is developed a occluded front where the cold front catches the warm front. And here it's getting a little long on the tooth. It's getting old. It's getting developed. It's going to dissipate because that occluded front is getting longer and longer and longer, and as it gets longer and longer and longer, that means more of the system is now stratified, and more stratification, cold on the bottom, warm on top, is going to lead to sort of a dissipation of the system. From a cloud perspective, if we jump down here to the bottom left, what we find is here's the cold front right here, right there. Here's our warm front right here, somewhere out here, right? And then up here at the top, swirling around, we have the occluded front. And so you can see different areas where there are and are not clouds. Notice everywhere up here by the occluded front is cloud covered. So in the wintertime, this is a place where you're going to get lots of snow, lots of heavy snow, and it's going to hang around for a long time. More severe weather coming in here where we've got the cold front, and then less severe but also precipitation involved with the warm front. And then you see like the areas like this back here where there's no cloud cover or very little cloud cover. And so this is a place where you have that continental polar air has pushed into the system. And so it would be kind of a cold and dry situation. And this area where there's no cloud cover, again, also down here is a place where you might have a warm air mass, in this case, sandwiched between the colds on the left and on the right. Here's some more examples of cyclones. This is on the left-hand side, we have the mid-latitude cyclone, right? Notice the shape, notice the distribution of or absence of clouds within the system, and notice that it is rotating in a counterclockwise fashion, right? Counterclockwise in the northern hemisphere, and it would be, again, opposite of that in the southern hemisphere. Also note that the low pressure zone is here in the center. That's where we see the lowest atmospheric pressures in the system, and that helps to drive this sort of counterclockwise rotation of the system. Come over to the right-hand side, and we see a picture of something called a nor'easter. Now, a nor'easter is developing between marine tropical and your maritime tropical, maritime polar and your maritime tropical air masses. And so again, you've got another kind of cyclone. You see different kind of cloud covers. This is a more developed picture than the one on the left, but the key is that it's air masses pushing in like this and like this. So the nor'easter is built on the intersection of air masses, but instead of coming from North America on the left-hand picture, sort of through the middle of North America like this, it comes in from the Atlantic. On the Atlantic coast, and it's called the nor'easter because the winds come out of the northeast. Okay, so it's another kind of cyclone that we see in North America. All right, so we can go ahead and do a little summary of the different weather fronts that we've had or that we've looked at, and how they're structured and organized as a way to think about this. We can sort of write this out, and hopefully this remains fairly clear. We've got the cold front, warm front, occluded, and then finally the stationary. Okay, so you really have four fronts involved here. Okay, and then we've got a boundary to think about, air masses that make up those fronts, clouds, and clouds lead us to thinking about weather and precipitation. So for the cold front, the boundary is steep. And so that means it's got a high angle, essentially. For the warm front, the boundary is gentle. That's right. For the occluded front, the boundary is actually kind of curved like this, where you have cold here and warm here. So I just call it a curved boundary. And for the stationary front, the boundary can be steep, but it doesn't matter as much because the air masses are moving past each other and they're not intersecting sort of directly in a head-on or catching up to each other or trailing each other. in this case, for the air masses, the cold air is for the cold front. What we're going to find is the cold air collides with the warm. Okay. For the warm front, we've got warm that does the colliding or the catching up to the cold air. Okay. At the occluded front, we see cold air masses. They meet and lift the warm air. Okay. And then stationary, I've already talked about this. We have side by side motion. Clouds for the cold front. I'm going to run out of space here, but nimbus, cumulonimbus clouds. Warm front, we're going to get a whole range from nimbostratus, so those are low layered clouds that extend along the front all the way up to cirrus clouds. Okay, the occluded front is a combo. It's a combo of all. So combo of both the warm and cold front clouds. So you'll find cumulonimbus clouds, but you also find all the cirrus clouds, depending on how you look at the cloud structure across these different boundaries. Okay, so it's a combo. And then at the stationary front, we don't have too many clouds because we don't have a lot of vertical motion. We have more horizontal motion of the air masses as they move side by side or past each other. But you could probably still find some clouds. That's not uncommon. In terms of precipitation at the cold front, it's going to be heavy. Okay? And it's going to be relatively short in duration, right? Thunderstorms might be 15 minutes, 20 minutes. Some of them last longer, of course, but that would be a version of kind of a cold front. And then you might have heavy snow for a few hours even. For warm fronts, you end up with long and lingering rain and precipitation. And for the occluded front, it's long and lingering and typically pretty heavy, because you have a mixture of both your cold and your warm fronts. Okay, and so we don't get too much rain and precipitation associated with stationary fronts as something that we need to worry about here. If you go take a meteorology class, it's going to go into the details of stationary fronts a little bit more and some of the weather conditions associated with them. But for our purposes, I think this should suffice. Okay, so that does it for our discussion of fronts and the development and evolution of the mid-latitude cyclone. I'm going to move on and we're going to watch some videos and talk a little bit more now in the final part 3, about severe weather and the connection between different kinds of fronts and the development of severe weather events.